Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper trending on X, published on July 8, 2025, just 2 days ago. This paper introduces a framework that improves image restoration, creating sharper and more detailed images with fewer artifacts, and it does this at Inference-Time, with no retraining needed. The paper is titled Kernel Density Steering: Inference-Time Scaling via Mode Seeking for Image Restoration, 2507.05604 v1, and as we'll see, the visual improvements are quite noticeable. Essentially, it guides multiple parallel image generation processes to learn from each other, avoiding common issues like blurriness or strange artifacts. Alright, so this first figure gives a great conceptual illustration of the method. It introduces kernel density steering, a technique where instead of generating one image, the model runs multiple parallel attempts, which are called particles. On the left, you see standard sampling, where these particles are independent and spread out, leading to varied and sometimes noisy results. But on the right, with kernel density steering, the particles learn from each other. They are guided towards shared, high-density areas. Basically, they find the most plausible solutions together, resulting in tighter clusters and sharper final images. Building on that concept, this next visualization shows kernel density steering in action on a simplified problem. The goal is to generate points that fall into one of three target zones, which are called Gaussian modes. The purple dots represent a standard sampling method called denoising diffusion implicit models, or DDIM, while the green dots show the same method with kernel density steering added. As the process unfolds, you can see the green particles being actively guided, eventually forming tight, accurate clusters right at the center of the targets, unlike the more scattered purple ones. Alright, so we've seen the concept, but what about the numbers? This table shows the super resolution performance on a couple of real-world datasets. It tests 3 different models with and without kernel density steering. You can see several metrics here. Some measure distortion like PSNR, where higher is better, and others measure perceptual quality, like LPIPS, where lower is better. And across the board, adding kernel density steering, shown here as plus KDS, consistently improves the scores. This quantitative data really backs up the visual improvements we saw earlier. Okay, and this table gives us a closer look at the super resolution performance on the DIV2K dataset specifically. We see 3 different models: LD-MSR, Diff-BIR, and C-Senior, each tested with and without kernel density steering. Besides the PSNR and LPIPS metrics we've already discussed, it also includes FID, or Fréchet inception distance, which gauges how realistic the generated images are. And the results are clear. Adding kernel density steering, here with 10 particles, improves the scores across the board. This consistent boost, regardless of the base model, really highlights its flexibility. So to wrap things up, we've seen that kernel density steering is a powerful plug-and-play framework. The key takeaway is that it improves image restoration at inference time, meaning no costly retraining is needed. It does this by using a statistical method called kernel density estimation. This helps a group of parallel image generations, the particles we talked about, find shared high-quality features. This collective process consistently produces sharper, more robust images across different models and tasks. That's all for this week's AI Research Roundup. Thanks for tuning in.